Welcome to Nerds at Church, a queer feminist podcast diving deep into faith, nerdery, and the Bible. I'm Pastor Emily, and I use pronouns like they, them, theirs.
And I'm Pastor Kay, and my pronouns are she, her.
And I'm Dr. Katie Mack, and my pronouns are she, her.
And in this episode, we'll discuss astrophysics.
Woohoo! Check out the episode description for links to any references we make in this episode. So, for our deep dive into astrophysics and the stars, we are excited, maybe quite possibly ridiculously excited, to have special guest Dr. Catherine Katie Mack, who is a theoretical astrophysicist studying a range of questions in cosmology and the study of the universe from beginning to end. She is the author of the book The End of Everything, Astrophysically Speaking, and holds the position of Hawking Chair of Cosmology and Science Communication at the Perimeter Institute for Theoretical Physics. Welcome.
Yes, we are so glad to have you.
Mm-hmm.
Thank you.
So, astrophysics.
Mm-hmm.
What is it?
We'll start off with an easy question.
Yeah. So astrophysics is a term that basically describes the study of things in space, but specifically like big things in space. So you can be somebody who studies space weather or something like that. That's a phenomenon that's sort of astrophysics, but sort of more like plasma physics, really. But astrophysics is like you're studying stars, galaxies, planets maybe, although planets are usually planetary scientists. So you're studying kind of like the big shiny stuff in space usually.
Nice.
Okay.
And really studying the physics of it. Now, the area of astrophysics that I'm in is cosmology, and cosmology is really like the absolute biggest question. So the evolution of the universe from beginning to end, the smallest scale physics, the largest scale physics, like how particle physics affects the nature of the cosmos, you know, the Big Bang, all of that stuff is in cosmology. And cosmology can also be kind of, if you study galaxies, but you only study the really, really distant ones, then that's also cosmology because the distant ones are in the far past, because light takes time to travel. And so the farther away it is, the farther in the past you're looking at it. And so cosmology covers all of that kind of stuff. But you can also be on the sort of way theoretical physics side of cosmology and study like hypothetical black holes that would form in space times with different numbers of dimensions, and that could be cosmology as well on that side of things. So anyways, I'm in an area that you might call like phenomenology, I guess, where so I don't ever deal with data. I'm not an observer, I don't do experiments, but I also don't make up new theories. I kind of sit in between and I talk to the people who are coming up with new theories about the universe or about particle physics, and then I talk to the people who are doing experiments or observations about particle physics or astrophysics, you know, like studying stuff in space, and I try and figure out how we can learn about the fundamental physics of the theory using the practical, you know, observations and experiments.
Ah, you're like the bridge that connects them.
Yeah, it's nice because it's a very creative space to be in, you know, kind of trying to make connections between different kinds of ideas.
Yeah.
And as a former philosophy major, that also sounds like you would probably have a lot of conversations with folks on that spectrum too.
You know, I only once went to a philosophy as a physics conference, and it was fascinating. And I'd never really dealt with philosophy of physics before that. But it was really interesting to look at things from that side. Because on my side, I mean, there are interesting philosophical implications to a lot of the stuff that I think about, of course, but I don't engage with that in my professional life. Sure. But it is really interesting to hear, you know, those kinds of discussions.
Yeah.
And you already hinted at this a bit, but what isn't astrophysics? Like, I'm imagining that probably people think that there are things that belong to that aspect of things and just aren't.
Yeah, so like space travel isn't astrophysics. You know, a lot of people connect astrophysics to like being an astronaut, and those are pretty different fields.
Sure.
Depending on kind of who you talk to and how you think about it, alien stuff is generally not astrophysics. That's astrobiology or sometimes planetary science or something like that.
Astrobiology? I didn't know.
Yeah,
that.
Oh, nice.
Yeah, astrobiology is a field. Yeah, like hypothetical at this point, but you know.
Anyway.
Although they do experiments on like, you know, trying to figure out how to make amino acids come together in a laboratory, so stuff like that. But that's generally something I would put sort of outside of astrophysics because it's more like it's sort of still astronomy, but it's not the physics of the physical systems per se.
Sure.
So when I get questions from the public, I get a lot of questions about aliens. I get a lot of questions about spaceflight. And I'm happy to talk about that stuff, but it's not strictly in my field.
Yeah.
It's someone else's job to invent warp drive, basically.
Yeah.
Nice.
And do astrophysics affect our everyday lives while we're down here on Earth?
Certain aspects of astrophysics can be important for life. I mean, so I talked before about space weather, which is only sort of astrophysics because it's kind of a little bit local. But, space weather can affect life. You can get auroras. Occasionally with a big solar flare, you can get kind of radio interference. So that kind of stuff can happen. Every once in a while, a rock falls down, and that can be, that's sort of astrophysics, sort of planetary science, but that can affect lives. Occasionally very drastically, usually not. Yeah. But yeah, other than that, astrophysics has a lot to do with how we all got here in terms of like the history of the planet Earth and the history of the stuff that we're made of. But there's not a lot of practical application to the stuff that I do. And I do the stuff I do because humans are curious species, right? Like we want to understand the universe, and I want to understand the universe, and the people in charge of making sure I have a job want to understand the universe. And that's why I do this stuff.
I'm pretty helpful.
You can come up with lots of justifications, like basic research in astrophysics and fundamental physics have a fantastic return on investment in terms of future technologies and all that kind of thing. Like Einstein's general relativity is part of GPS systems now, and they wouldn't work without it. And there's a bunch of examples you could go on for days about places where, total blue sky research has turned into practical technology decades, centuries down the road. So possibly some of the stuff I work on will have those applications, but really I do it because people want to know stuff, and I want to be part of that.
Yeah.
That's a good reason.
Feel that a lot. Yeah.
And you also anticipated this question a bit, but I always wanted to ask an astrophysicist. When I heard the word astrophysics the first time, I thought of the standard variety of science classes most people take in high school, biology, chemistry, physics, and asked myself, so if there's astrophysics, is there also astrobiology? Is there also astrochemistry? And it sounds like that's a yes.
Yes, absolutely. Yeah. I have a good internet friend who's an astrochemist. Yeah, all this stuff happens. Like I said, astrobiology is more or less theoretical at this point, or experimental, but not observational. But astrochemistry is a huge deal where it's all about, we study the chemistry of other stars, occasionally other planets, by looking at the patterns in the light that we get from them from the spectrum. So, as the light is passing through clouds of different kinds of material, the different chemicals absorb the light in different ways, and you can see that imprint in the spectrum of the light that you get from these objects. And so you can learn a ton about the chemistry of other stars and planets. And in the context of stars, it's really interesting because, as a star forms and evolves and burns and explodes, it does nuclear physics inside and changes elements into other elements. And that's how you get heavy elements and the stuff that we're made of. And so understanding the chemistry of these stars can tell you a lot about sort of the history of star formation and galaxies and the history of the universe in really interesting ways. And then also like how galaxies work and how stars work, and all of that kind of stuff comes out of an understanding of astrochemistry. So it's a really important area.
When we're thinking about like the tree of academics, I don't know if you think about it as a tree, but I'm thinking like family tree style. Okay. All of those then fall under astronomy?
Sort of, yeah. Yeah, it's complicated. There's like complicated Venn diagrams going on. So yeah, they're all in some way under astronomy. Some of the people I work with in my field in cosmology would not class themselves under astronomy at all. They would put themselves under physics, but not astronomy. And it's sort of cultural, like, how you approach questions and what kinds of tools you use. But yeah, astrochemistry, astrobiology, that all comes under astronomy, broadly defined, sure.
Okay, sure. Cool.
I suppose since we don't currently do a lot of space travel, it makes sense for us to sort our science into Earth science and like outside of Earth science. But eventually, maybe we will get to the point where those sorting systems don't work anymore.
Yeah, I mean, planetary science is kind of an Earth science thing, right?
Yeah.
But people are actively studying other planets, and maybe eventually we'll go to some. I mean,
sure.
Depending on whether you consider going to the moon being a kind of planetary science, but
sure.
There was a geologist who was sent, so
right.
At least one.
Yeah. So what is your favorite thing or like phenomenon in space to study?
Well, my main area of research is about dark matter, and I'm very excited about dark matter. So
Me too.
yeah, so dark matter is a very cool sort of mystery. Essentially, when we look at galaxies out there in space, like we're a spiral galaxy shaped like a disk, got spiral arms. The Milky Way is a spiral galaxy. When you look at a galaxy like that, like the Milky Way or like other similar galaxies, you see the stars and the gas and the dust, all the stuff that glows, but something like 80-85% of the matter that's contained in the region of that galaxy is actually totally invisible, and it's called dark matter. And most of the matter in the universe is this dark matter, this invisible stuff. And we have really good reason to believe it exists because of the way that it affects the motions of galaxies, the way that it affects even the bending of space, because of, in Einstein's general relativity, his theory of gravity, the way gravity works is that a massive object bends the space around it, and that causes trajectories to change, and it causes light to move around in different ways. And we see that phenomenon happening with visible massive objects, but we also see it happening with invisible massive stuff like dark matter. And so we have tons of different ways to know that dark matter is out there and that it's most of the matter in the universe, but we can't see it. It seems to be invisible, and that invisibility it's not just that it's like dark. So like it's called dark matter, but it's not black or something like that, because that would be absorbing all the light. It absorbs none of the light. All the light just passes through it. And we think that basically what's happening there is that when you see something, it's because photons, particles of light, are interacting with that thing and then interacting with you, reflection or absorption or emission. We think that dark matter just doesn't deal with photons. It doesn't deal with the electromagnetic force at all. So photons are particles of light. They're the carriers of the electromagnetic force. We think that dark matter doesn't do that. And because of that, it's also untouchable, because when you touch something, what you're doing is you're pushing your electrons against the electrons in the other thing, and they're repelling each other with electrostatic forces. And so if you don't have electromagnetism, then nothing feels solid. And so dark matter can pass through itself and other matter without interacting, at least the vast majority of the time. And so that causes it to be distributed differently. It means you can't see it, you can't touch it. Makes it very hard to detect.
Yeah.
So we have hope for ways of detecting dark matter that don't deal with electromagnetism. So there are other fundamental forces of nature, and we might be able to detect dark matter through other kinds of interactions, like the weak nuclear force. Maybe dark matter has an interaction with the weak nuclear force, and that would be a very rare interaction, a very weak interaction. But if we build the right kind of detector, we might be able to find it that way. So there are a bunch of different ways that we try to identify what dark matter is made of, but we also have just a ton of evidence that it's out there. We can map it. We can, figure out the shape of it, what it's doing. And part of my work is trying to come up with new ways to identify it.
That is fascinating. Because, as we were talking, I was like, what other ways? And I was like, infrared is on the electromagnetic, like everything that was popping into my head of like microwaves and like all of the things that we use right now to detect space are electromagnetic spectrum stuff.
Well, there's one we use that's not an electromagnetic thing, which is gravitational waves. It's very new, but we do now have detectors that can detect when really massive objects in other galaxies move around in certain ways and cause ripples in the fabric of space, basically. And we're able to detect those. That might also be something that can tell us about dark matter. And I've been involved in some research to try to figure out how gravitational waves can give us information about dark matter too. So there are some other creative things we can do.
Which, that makes sense, because matter and gravitation, or gravity, or gravity, depending on where you are at in the Doctor Who universe. But
the basic idea is that with gravitational waves, we're mostly looking at black holes that spiral around each other and then collide. But if dark matter is doing different things, it could affect how those black holes come together. So
sure. I'm realizing, I think the last time I read an explanation of dark matter, they were focusing entirely on dark matter out there in space, far, far away from us. And now that I realize that we have such limited ways of knowing where it is and what it's doing, the idea that dark matter could be like moving through me right now is a little unsettling. So I see.
Oh, it almost certainly is.
Okay.
It's almost certainly moving through us right now. Yeah. No.
Okay.
Solid.
More correctly, we are moving through this giant cloud of dark matter that our galaxy is embedded in, right? So the sun is moving around the center of the galaxy. It takes millions of years to make a circuit, but as the galaxy rotates, the sun is moving around, and the galaxy is embedded in this just giant blob of dark matter that's kind of mostly spherical, more concentrated at the center, but anyway. And so as the sun moves around and drags us with it, it's moving through this dark matter, and so we are constantly moving through the dark matter, and it doesn't interact with us, so yeah.
Wow. Okay, that's like a whole mind blown thing. And
yeah.
Wow. Okay, so we've talked about dark matter. A lot of times when we talk about dark matter, we also talk about dark energy. But dark matter and dark energy are different things.
Yes. Yeah.
Can you get into that just a little?
Yeah. No, that's a great question, because a lot of times people assume that they're related because they're both called dark, and one is called matter and one is called energy, and people are like, oh, they must be related by E equals mc squared or something like that. But those terms are really just like, they're both called dark because we can't see them and don't know what they are. That's as far as their connection goes, as far as we know. There are some theories that involve, connections between dark matter and dark energy, but as far as we can tell, they're totally unrelated phenomena, absent evidence to the contrary. So dark matter is this, kind of invisible stuff that holds galaxies together. Dark energy is a term we use to describe whatever is making the universe expand faster. So the universe is expanding. It's been expanding since the beginning. And for billions of years, that expansion was kind of slowing down because essentially, everything's kind of moving away from everything else, but everything also has gravity and is pulling toward everything else. And so that kind of put the brakes on the expansion to some degree. And so the expansion was slowing down. And in the 1990s, there was this effort to try to figure out how quickly that expansion was slowing down, to find out if it would slow down and stop and then reverse and cause a big crunch, or if it would just keep, if the expansion would continue expanding forever, always slowing down a little bit, but, and it's basically the same question as, like, if you throw a ball in the air, you throw it into the air, you give it that initial push, and then it's always slowing down because the gravity of the Earth is pulling on and the gravity of the ball is pulling, and so it slows down because of that. And generally speaking, you can't throw it hard enough for it to not stop and come back. If you could throw it at 11.2 kilometers a second escape velocity, then it would just continue going forever, but it would always be, slowing down a little bit because it'd be affected still by the Earth's gravity. And so basically it was the same idea with the universe. There was the Big Bang, something happened, set off the expansion, and then everything's been kind of drifting since then, and everything's expanding, but everything's moving away from everything else, but still pulling together with gravity, and so that's slowing down. And so there was this question, are we in the case where, you throw the ball, it stops and comes back, or are we in the case where you throw the ball hard enough, it keeps going forever? And what they found when they did the measurements was that the expansion was not actually slowing down at all, it was speeding up, which was very unexpected at the time.
Yeah.
And now we know that, for many billions of years, the expansion was slowing down, and then something like 5 or 6 billion years ago, it started speeding up. And the physics of that is if that happens with a ball, if you throw a ball in the air and it slows down for a while and then shoots off into the sky, then something happened.
Yeah.
It wasn't just gravity and falling. There must have been a wind or something like that. And so we had to revise our theory of how the universe works to add something that could make the universe expand faster, that could counteract that gravity, to add a push to the expansion. And whatever that is, we call it dark energy. And we have some ideas about it. One is that the sort of most accepted idea is that it's something called a cosmological constant, which is just there's this extra kind of stretchiness built into space, so that when space gets bigger, it wants to get even bigger. And that's just a term that's in the equations, basically. But you can think of it as there's this little bit of stretchiness in space. And so the reason that things were slowing down for such a long time was that, that stretchiness was still there, but the gravity was stronger. But then when everything got far enough apart that the gravity was no longer pulling as hard, then that stretchiness kind of took over and became the dominant force. And so that's why, as of cosmically recently, the expansion started speeding up. And so anyway, dark energy is something that seems to be totally uniformly distributed through the cosmos. and is invisible, and all it does is make the universe expand faster. Whereas dark matter is like clumped where galaxies are, and it pulls matter in rather than pushing it away. So they're kind of opposite in a lot of ways. Dark energy is a lot harder to study because all you can really study is the expansion rate of the universe, or like how quickly, galaxies and clusters of galaxies came together in the past, like the growth rate of structure. But you can't map it out because it's the same everywhere as far as we can tell. Yeah. And there's a hope. I mean, people look for evidence for dark energy being something other than a cosmological constant, something that could like change with time in some interesting way. But so far we haven't found any evidence of anything other than like, well, I guess space is a little stretchy and that's just how it is. It's a tough problem, though, because we don't have any fundamental theoretical basis for why that term should be in the equations and at the number it is. So it's a big mystery, but it's much harder to study than dark matter because it just doesn't do as interesting stuff as dark matter seems to.
Yeah, that's fascinating. And dark matter is also the stuff that like keeps galaxy clusters clustery.
Yeah.
Right?
Yeah.
Okay.
Yeah, kind of anytime you see like matter clumped together in the universe, dark matter is like most of the kind of glue that's allowing that to happen. You can go through the sort of history of the universe, and without dark matter, it would have taken much longer for galaxies to form initially. We wouldn't have our galaxy the way it is, because basically if you throw a bunch of regular matter at other regular matter, it'll like heat up and puff up because it collides and gets messy. Dark matter doesn't have that. So if you have a big clump of dark matter and you throw some regular matter in, it's more able to hold together. And so so dark matter allows structures to form more quickly and more clumpy in some ways. And so, yeah, galaxy clusters are mostly dark matter. Galaxies are mostly dark matter. On the scales of like stars and planets, dark matter becomes unimportant because although dark matter is most of the matter in a galaxy, it's not in a solar system. Just because when you throw regular matter at regular matter, it does puff up and stuff, but it also can like radiate energy through those like collisions of particles, and then it can get more and more concentrated. Whereas with dark matter, you throw two clumps of dark matter at each other, they pass through and they might spiral around or whatever, but they don't become really, really
They don't
compact.
get stuck together.
Yeah, they don't get stuck. And so you can have really compact objects like stars and planets with regular matter, and it doesn't seem to happen with dark matter. It kind of depends on the model of dark matter you're dealing with, and there are some that have that happen to a limited degree. But as far as we can tell, for the most part, dark matter is very, very diffuse, and so it only becomes really important on galaxy scales. So in our solar system, there's very little dark matter. Just we're much more of a regular matter kind of place
sun
here.
And Jupiter. And,
Yeah. So a friend of mine, Randall Monroe, who writes the XKCD comics, he calculated that like there's about the mass of a squirrel of dark matter in the Earth or something like that. Like it's a very small amount in our sort of local volume.
That's fantastic. Okay, so this is just fascinating. We are in our podcast season 4. We are doing a season of Epiphany, which gives us the space to talk about space. And I know it was pun intended.
These things just happen to you.
I know they do. So we actually did an episode on cosmologies from not a scientific perspective, but a cultural and theological perspectives on cosmology and stuff. And there's many theories of what it was that led the Magi to Jesus after he was born. In scripture, in Matthew, it says they followed a star. Some people say it's a comet. Some people say it was an asteroid. Some people talk about the astrological alignment of Venus rising into Pisces. And some say it was a supernova. So we've talked about what we're not seeing when we look into the sky, but what are we actually seeing when we get far enough out of cities to look up at night and see things?
Well, yeah, all sorts of stuff. I don't get to go to dark sky places very often, but I have been a few times, and it's really different. You can actually see the night sky, because I grew up in Los Angeles, and the sky at night is pink.
Yep.
And it's just not you don't get a lot of those kinds of stars in LA. But if you go out to like a really dark sky place, then you see the Milky Way galaxy. That's the most striking thing, is that you see this like a pale white stripe across the sky. And that's because we live in this disk galaxy. And so, while you're inside the disk, if you look within the plane of the disk, you see it as a white band. And in the northern hemisphere, it's quite striking as this sort of pale white band across the sky. In the southern hemisphere, you're looking toward the center of the galaxy. And so you can see the bulge of the galaxy, which is the sort of the center part where it's a little bit brighter and there's a little bit more going on. And it's very spectacular. And so that you can see the brightness of the center of the galaxy. You also see, patches of darkness within that brightness that are from dark dust clouds between us and the center, or really us and like other parts of the disk. And you can see some of those in the north as well, I think, but I've only seen them really in the south because I lived in Australia for many years, and I've got to some really dark places there, which is very cool.
Wow.
So you can see the Milky Way, which is just really the sum of the light from the stars within the disk of the galaxy. The stars that you can see individually are mostly within sort of a few hundred light years of us, which is not huge. The whole galaxy is about 100,000 light years across. So the ones that you see nearby are really pretty nearby. So a light year, in case anybody's not aware, is the distance light can travel in a year. And it's a very long way. I don't remember the numbers off the top of my head. But for context, the sun is 8 light minutes away. And the moon is 1.3 light seconds away. So a light year is very far.
Yeah.
The nearest star to us that isn't the sun is about 4 light years away. And that's also something you can see from the southern hemisphere, Alpha Centauri. So anyway, you see a bunch of stars, you see the galaxy. In some cases, in some places, in some really dark circumstances, you can see other galaxies. There are only a few of them that you can see with the naked eye, but in the north, it's Andromeda is the big one. And the Andromeda galaxy is our nearest neighbor, large disk galaxy. And it's, I don't remember, some number of millions of light years away, maybe 65. I don't know. I have to look it up, or 2. I have to check. Anyway, the Andromeda galaxy is millions of light years away, but you can see it very a little bit in the north, and if you have a really dark sky at certain times of year, and generally it'll look like a little fuzzy blob. You can't see with the naked eye very much detail. In the south, you can see a couple of satellite galaxies of our Milky Way, the Magellanic Clouds, so the large and the small Magellanic Clouds, which are little galaxies that orbit the Milky Way, and they're quite striking if it's dark enough. They look like clouds, basically. They look like little white fuzzy blobs, but much more striking than Andromeda. So there's those things.
Also, I Googled while you were talking. Andromeda is 2.537 million light years away.
Okay, 2.5 is the right number, yes. Okay. Anyways, very far. But it's interesting, fun fact, Andromeda is heading toward us.
Oh, fun!
It's coming toward us at 110 kilometers a second, and in about 4 billion years, it will collide with the Milky Way and totally restructure the whole galaxy, and it'll be a big mess and a big light show, and we will, of course, be gone by then. In some one way or another, because 4 billion years is about when the sun is expected to kind of die in one way or another. But in only about 1 billion years, the sun will be bright enough to boil off the oceans of the earth. So that's I don't know, maybe I should just throw that stuff out there. But anyway,
immortality.
I think we're going to get to that in a couple questions, but yeah.
Yeah, so you can see Andromeda coming for us. You can see other stars, stars around the Milky Way nearby. You can see globular clusters, which are like clusters of stars, very old clusters of stars that have lots of old stars that are sort of very concentrated little clusters of stars in sort of spherical blob, more concentrated in the center. You can see clusters of stars that are star-forming clusters, where stars are being born. You can see nebulae, which are blobs of gas and dust that have sort of a cool glow because of the chemistry inside those clouds. Depending on what's going on, you might see a comet or an asteroid. Usually those are hard to see with the naked eye, but depending on what's going on, you might see something like that. And if you're very lucky, you could see a supernova, but we haven't had a naked eye supernova in a very long time, so it would probably be a while. But Yeah, so mostly stars, but a couple other cool things sometimes.
Yeah, and naked eye, you can see the moon, obviously, but...
Yeah, the moon, yeah, planets. So in terms of planets, yeah, so you can almost always, if it fits up, Jupiter, Venus, Mars, and Saturn are the ones that are quite easy to see with the naked eye from anywhere if they're up. And depending on the time of year, of course, like right now, Venus is about to go behind the sun for a while, so we won't see it for a bit. But Jupiter is very bright these days, and if you see a really bright dot in the sky, it's probably Jupiter at this point. And then if you have a really dark sky, or if you're very lucky, or if you have a telescope, you might see some of the other planets. So like Neptune and Uranus and Mercury. Mercury is sometimes a naked eye object, but you have to be careful because it's close enough to the sun that it's only ever visible right before sunrise or right after sunset. And you have to make sure you don't look too much at the sun. Like, you have to not look at the sun.
That would be fun.
But it's very close to the sun.
So we've talked about like galaxies and planets and dark matter and dark energy. How do black holes factor in? Like, are they one of...
Good question.
Yeah.
So there are theories about dark matter in which dark matter is made of very small black holes. Those are kind of not the favored theories, but they haven't been ruled out. So there are certain mass ranges for, hypothetical little black holes where they could make up all the dark matter. The problem is we don't have any confirmed mechanism for creating little black holes. So generally speaking, a black hole is what happens when a massive star runs out of fuel to burn and collapses on itself, and it turns into a black hole. And those kinds of black holes cannot account for dark matter. They're too massive. There are reasons why we would notice if those black holes were dark matter. Mm-hmm. So you would need some mechanism that created a bunch of very, very small black holes early in the universe. And we don't have an accepted theory that does that. There are lots of speculative theories that can make what are called primordial black holes, where something happens in the very early universe around the Big Bang and creates a bunch of little tiny black holes, and then those black holes could appear as dark matter later on. But again, we just don't have a model that's like an accepted model that does that. There are just a bunch of hypotheses. So yeah, I mean, black holes are basically a stellar phenomenon, because the ones that we know about, they form at the end of the life of a star. That said, there are also supermassive black holes, which are very, very massive black holes that live at the centers of galaxies. So for example, the center of our galaxy, the Milky Way, has a 4 million solar mass black hole at the center, so 4 million times as massive as the sun. It lives at the center of our galaxy, in the middle, in the bulge. And we don't entirely understand how those black holes form. Most large galaxies appear to have at least one supermassive black hole in the center. Sometimes there are two because there's been a collision of galaxies and the black holes haven't merged yet. But generally speaking, there's one at the center of every large galaxy, and they can be up to billions of times as massive as the sun. And we don't have a consensus on how they formed, because it's quite hard to, just through like a star collapses, creates a stellar mass black hole, and then stuff falls into that. It's hard for that process to happen efficiently enough to create black holes that massive that quickly. Like, we have evidence for black holes that are millions of times as massive as the sun within the first few 100 million years of the universe. And it's just hard to get that much material together that quickly. Mm-hmm. So, again, there's theories, there's modeling around how to do it, but there are lots of interesting ideas for making black holes that massive that quickly. So the formation channel for the supermassive black holes is still kind of under investigation, but all other black holes, just like the regular ones that happen because stars collapse, they're just, the end result of certain kinds of stellar collapse. So that said, our sun is not going to create a black hole. It's not massive enough. When our sun dies, it'll create what's called a white dwarf star. Mm-hmm. So basically the center of the sun will become this very compact object called a white dwarf. The outer layers of the sun will be kind of blown away. It'll make a pretty nebula, and then it'll just kind of cool forever. And then if our sun was a little bit more massive, then it could go supernova and then leave either a neutron star, which is a super, super dense object, or a black hole, which is, a black hole, mm-hmm. as the result. But for our sun, it's not going to, it's just going to be a white dwarf.
Interesting.
And it's not going to explode.
Well, unless something interesting happens with Andromeda, I suppose. But if it gets hit by something.
Well, yeah.
It's the timing.
So it's possible. So white dwarfs can explode as supernova, but only if they gather a whole bunch of material from something else. So generally speaking, you can have like two stars that are in a mutual orbit, a binary system. And if one of them's a white dwarf and it's pulling material off the other, then that can get to a point where it basically reaches a critical stage of, like, it gets too massive and then it explodes and becomes a supernova that's called a type 1a supernova, if you're interested. But so it's feasible that after our sun becomes a white dwarf, something like that could happen to it. But I think it would be hard to get that to work out perfectly.
The probabilities are...
But it's a good point that after Andromeda comes for us and the sun, becomes a white dwarf, and then all the orbits are all messed up because everything's all mixed up in this kind of, mixer of the collision, then sure, it could gain a companion and eat it and become a supernova.
Now I'm just picturing like the sun as a white dwarf with like a giant mouth just like chomping.
Yeah.
Pac-Man.
Miss Pac-Man style. That's fantastic. Okay, so what is your favorite or like the most exciting moment that you have experienced in astrophysics?
It's a good question. I mean, there have been some exciting moments of like announcements of big discoveries, right? So there was the Higgs boson discovery, and that was in 2012. And at that time, when that happened, I was an instructor for a summer, a summer camp for high school kids doing astronomy in Spain. So I was hanging out with a bunch of kids, and we watched the discovery on a projector screen in a lecture theater, and that was kind of cool, watching the announcement that they discovered the Higgs boson.
So for people who are like, Higgs boson,
yeah,
I've heard that word.
Yeah, so the Higgs boson is a particle that's... So essentially, we have what's called the standard model of particle physics, and the standard model of particle physics is like it's all the electrons and the quarks, which are the particles that make up protons and neutrons, and the all the things that carry the forces of nature, like the photon with the electromagnetic force and the gluon for the strong nuclear force, stuff like that. All these particles that we know about, neutrinos, and the Higgs boson is like the last missing piece of that model. And the Higgs boson is a particle that's associated with the Higgs field, which is this kind of energy field that goes through all of space. And basically, particles interacting with the Higgs field is part of how certain particles have mass. It's a long, complicated story, but the Higgs field is connected with certain particles having mass. It's connected with a process that happened in the very early universe that created the conditions for our current understanding of particle physics. It created the possibility for particles to have mass in the very early universe. So it's kind of just a big piece of our understanding of how particle physics works. And the discovery of the Higgs boson, which was discovered through, particle collisions at the Large Hadron Collider and looking at the debris from particles colliding at this particle collider, that kind of confirmed our understanding of the standard model of particle physics and how particles came to have mass in the early universe. And it's something that had been, we'd been looking for that for decades. Like, this experiment had been planned for many decades, and we were all waiting to see if the Higgs boson would be discovered. And so when it was a really big deal for physics and astrophysics as well. So anyway, so that was a big deal. I remember that very clearly. The other one that I would say was really exciting was when the first gravitational wave discovery was announced. And that was in 2017, I think. And that was, I remember that too, because I was in Australia and I was doing a postdoctoral fellowship in Australia. And so the announcement was at like 2 a.m. local time. And a bunch of us postdocs and grad students got together at some conference room at the university, somewhere in Melbourne. Anyway, we got together and like watched the announcement and like ate donuts and just had a party, basically.
Nice.
But that was cool because that was the first discovery of something that, like, it's a whole new way of looking at the universe, right? Like it's like being able to feel the vibrations of space itself and using that to learn about the invisible cosmos. I mean, it was very, very cool.
Yeah, especially for particularly dark matter stuff. And
yeah, potentially, yeah.
So, speaking of astrophysics.
Okay.
I'm bad at transitions. I have a shirt. It says 2NB to transition. It's a real problem I have. So what actually is the end of everything, astrophysically speaking?
Right. So the book is about different possible ways the universe might end. And there's a standard kind of accepted theory for the most likely way the universe ends, and it has to do with dark energy. Dark energy is probably a cosmological constant, so it's probably just something that, exists in space and just is part of how space works. And if that's true, then the end of the universe is going to be when everything has diffused so much through space and all of the matter has kind of decayed away and there's just nothing interesting left, and the space becomes cold, dark, and empty and, kind of meaningless. And that's called the heat death of the universe. And heat death is a term that has to do with everything evolves into waste heat, and then you maximize the entropy, the disorder of the universe, and that's the heat death of the universe. So that's the most likely scenario for the end of the universe based on our current understanding, but there are a number of other hypotheses that have been explored in the past or that are being considered now where different kinds of things could happen. And so the book that I wrote is kind of walking through those different possibilities and why they were proposed and how we think about them and so on.
Nice. Do you have a favorite?
I do. My favorite is probably the hardest to explain, but it's called vacuum decay.
Oh.
And this is, so I talked about the Higgs field before, so this kind of energy field that's through all the space, and in the very early universe, there was a transition, a change in the Higgs field, and that change set up the conditions for particle physics to exist the way it does. So it allowed for particles to have mass, for the electromagnetic force to exist, so that atoms could form, and then molecules, and so it set the scene for the state of the universe that we live in. And there's this hypothesis that maybe the Higgs field could change again. And that would be bad because that would change all the laws of physics and make it impossible for our atoms to hold together and just destroy the whole universe. And that process, if that happens, is called vacuum decay. And so that's my favorite ending of the universe because it's just very dramatic and sudden and unpredictable and very clean. It just destroys everything. And it's kind of a cool connection between particle physics and cosmology. Yeah. But every time I talk about vacuum decay, I have to put in a disclaimer that although this is something that is hypothesized, and if it were possible, it would be something that would not be predictable exactly sort of when or where it would happen, it is not something to worry about. So please do not lose sleep over the idea that the universe could suddenly end. All of our current understanding is that if it is even possible at all, it's very unlikely to happen within the next 10 to the power of 100 years. So very, very long from now, if it were to occur. And also our theories are so incomplete that we can't say for sure if it can occur or not. So please don't worry about vacuum decay. I do get emails from people saying that they can't sleep anymore. They're filled with anxiety. Don't do that. Yeah. It's fine. Worry about climate change. And don't worry about vacuum decay.
Great.
Yeah. It kind of sounds like it's more likely that a sinkhole would open up underneath your house and swallow you than vacuum decay.
Oh, yeah. I mean, in terms of probabilities, it's more likely that you'll be, hit by a meteor while also killed by a runaway train somewhere not near a train track while winning the lottery. It's just,
sure.
There's so many layers of probability. Yeah. That's not going to be what kills you in this life. So do not worry.
Good to know.
Yeah.
I also like that, though. I really like that theory. Partly, too, because everything, gets all flipped and is all this other thing. But that also creates the possibility of something new. Some new way, right? Or no?
Maybe.
I don't know. If it came together, if it, did this thing to come together, and then, it's going to do this other thing and totally mess up everything about the way we understand the world and the universe and stuff, then it could create some completely other bizarre context for which things could happen.
Sure, but
not really.
I have to tell you, so some of the people who were first kind of studying this possibility in the 80s, when they were doing the calculations, they were working out the consequences of the potential for vacuum decay. And they did the calculations and they found that once this transition occurs, if it does occur, the space within the kind of true vacuum bubble, the thing that's expanding out and destroying the whole universe, that new space with the new laws of physics becomes gravitationally unstable in a very short time scale. And so once you're inside that bubble, you collapse into a black hole.
Okay.
And so, like, it's not entirely certain that that would happen based on our current understanding, although I think it's still kind of the favored model. But I gotta read you just a little snippet of that paper where they calculated this, because it's a direct response to what you just said.
Okay.
So they do this calculation where it says that the inside of the bubble would be unstable, and they say, this is disheartening. The possibility that we are living in a false vacuum has never been a cheering one to contemplate. Vacuum decay is the ultimate ecological catastrophe. In a new vacuum, there are new constants of nature. After vacuum decay, not only is life as we know it impossible, so is chemistry as we know it. However, one could always draw stoic comfort from the possibility that perhaps in the course of time, the new vacuum would sustain, if not life as we know it, at least some structures capable of knowing joy. This possibility has now been eliminated.
Oh no. My gosh, they just wipe it off completely.
Yeah. Oh. Yeah.
Okay.
Suddenly I understand those people who are having trouble sleeping.
Right, yeah. So that's from Coleman and DeLucia from 1980. And as I said, different models, you can get kind of different answers for that. But I love the way that they wrote that out, being like, oh no, don't be comforted. No, we thought there was an upside, but no, there's not. Sorry. It's just bad.
Thank you for dashing my very, very brief hopes.
I'm sorry.
It's okay. Is that paper accessible?
You can find it. I mean, the prose is very well written, but it's a technical paper. So it's 1980, Coleman and DeLucia. I can send you the link if people want to look it up.
That would be awesome. That way we can link to it and people can have the option. We're doing a book list for this season anyway, so having book/resource list. So we're putting in all of that stuff.
I think it's called Gravitational Effects on and of Vacuum Decay, I think is the paper. I don't know, I'll have to check.
That's right, yeah. Awesome.
So we don't get a lot of people who do higher math on the show so far, but I have a feeling that we have some listeners who have been, emotionally scarred by their math teachers in the past, because I've known a lot of people who went through that. And I've also heard from a few folks who do higher math professionally that the kind of math that you do in astrophysics feels very different than the stuff that our high school math teachers may have emotionally scarred us with, like geometry. It isn't
geometry
as well. Yeah, it's not as nitty gritty. I think the way my friend who is now a math prof put it is that it really does have a different feel to it. It feels like a different type of field. And so can you speak to that at all?
So, yeah, so the area I'm in, theoretical cosmology, it's basically all math, right? So I don't know if you've seen the movie Don't Look Up. It's a fun movie. It's an allegory for climate change, but it's about this idea that there's a killer asteroid coming for the Earth, and these scientists are trying to convince the public to take it seriously. And at one point, this sort of press person, the sort of press consultant, is talking to the scientists about how to talk about these things on the TV shows, and the guy's telling him just tell the story, no math. And the scientist is like, but it's all math. and I mean, and as a theoretical physicist, the whole point of theoretical physics really is to create a mathematical model for the stuff that we observe, right? So we build, I think of it as a mathematical cartoon that represents the observations that we have. So we have some amount of data, you could have data for the height of a ball after you drop it after a certain number of seconds, and you create a model where if you put the time into that model, it tells you the height of the ball right? And that's just a model, and there's always some degree of approximation, right? In this model, you might assume that there's no air resistance and there's no wind and the ball is perfectly smooth and, all of this kind of stuff.
Sure.
And the surface of the earth is perfectly smooth and the gravitational constant never changes as you go over a mountain, like whatever, right? And so there's always some degree of approximation. But the whole point is we create a cartoon built of math to describe what we observe in the universe. And so so all the time it's math that you're dealing with in one way or another. And so, so some facility with mathematics is certainly important when you're doing any kind of quantitative science. And even, any area where you're dealing with data, statistics, you have to get some facility with mathematics.
You got to be able to tell people the probability of utter destruction is very low, right?
right. Yeah, that's helpful. Yeah. But I certainly know a lot of people who say that, they love physics, but they're not good at math. They're not a math person. And when I hear that, I always think I try and tell them there's no such thing as a math person, right? If you're really interested in something and you spend a lot of time doing it, you become better at it, right? Nobody is born a music person, but they practice their instrument and they become good at it, right? Or, a sports person. You can start out with different advantages or disadvantages, physically for things that you're trying to do. But if you practice and work hard and, devote a lot of time and effort, you can improve at basically anything. And mathematics is one of those things that if you put a lot of time and effort into it, like learning a language, then you will become better at it. And so, I think a lot of times what happens is people are in school and they try to do something in mathematics and maybe they don't have a very good teacher, or maybe they just kind of don't have confidence and they find it difficult. And then because of the messages that society sends about genius and stuff like that, they assume I'm just not cut out for this. I'm just not a math person. I can't do this. And so then they get this impression that it's impossible to get better. And I find that really sad when I see that. And especially a lot of times it happens too with kids that they'll be really interested in a topic, but they find it really difficult to, do it in an academic way. And so they assume that if it's difficult, that means that they shouldn't do it, that they should only do the things that they are natural at. And that's just totally wrong. Physics is hard, mathematics is hard, and you do have to put in effort. Right?
Yeah.
I've had to put in effort at every stage in my career. I've had to work hard. It did not come to me as, sort of just a magical thought in my brain. I had to learn it. I had to study. I had to practice. And I became better at the things that I put a lot of time and effort into. Yeah. And I was never such a natural that I could just not try. And yet I'm a professional astrophysicist now, right?
Yeah.
It can be the thing that you should do, even if it's hard.
Yeah.
And so I try to really emphasize that, especially with children, that having to try does not mean that it's not your thing.
Yeah.
Right?
And I think the flip side to that, right, is also people are told if you're good at something, that is what you should do. And just because you're good at it doesn't mean that's what you should do or you're in church speak called to do.
Yeah.
And so since we are nerds at church, let's spend a few moments talking about the Bible. We came up with a couple of readings talking about God creating the universe, stretching out the heavens, and also including God's own holy darkness of the universe. And so our first passage is Isaiah chapter 45, verses 7 and 8, 11 and 12, and 17 through 19.
And for those of you who are clicking the link, we also have the whole of the Isaiah 45, 7 through 19 linked, just so you get the context, because we like context as nerds at church, but also didn't want to include all 12 verses when it's really more of a scattered throughout in Isaiah type of thing, just so you know. But also so this is one of the spaces, right, where science and church, science and faith, we very frequently think about it as absolutely different things and never the twain shall meet kind of situation. And obviously on this podcast, we meet the two a lot because Kay and I are nerds and pastors, and that is kind of how we do. But also our guests have different perspectives. So as we get into these, if you would like to share some of your own perspective on your own journey of how you came to be in your current belief cosmological system thing, we would welcome that. So in Isaiah, I really love, particularly in verse 7, where there's this play of like God saying, I form light and create darkness. And that concept that like God has created everything. God has stretched out the heavens, the stars, the galaxies, the whole cosmos. And for me, when I look at like pictures of space or like the Atlantic's Advent space calendar, it really brings this poetic kind of awareness of and like wonder and awe at space and like the cosmos, the like source and ground of all being and light, which is like a way that we sometimes talk about God. Yeah, I really just love that space.
Yeah, I looked at verse 7 and I thought about how this verse talks about God creating the entire spectrum of all possible experiences, because in the Hebrew language, as Emily can tell you, being our resident expert, when you get the list of I formed light and created darkness, it's not just that God created those two separate different things, it's that God created the full spectrum between them.
Mm-hmm. It's a merism for language nerds. A merism.
And also God then firmly locates where to look for God and who God is in the easy to find place in verse 19. God is not hiding from us. God is accessible.
Yeah. I like the accessibility in that spot. Doesn't always feel accessible, but yeah. Our other reading that we looked at was Colossians chapter 1, verses 15 through 17, which is mostly talking about Jesus. And I really liked the first half of verse 16. I like all of it, but the first half of verse 16, where the author writes, For in Christ all things in heaven and on earth were created, things visible and invisible. And we have been talking a lot about the visible and the invisible in an astrophysical sense. And so like thinking about that, both in terms of like there are things that are so small that they are invisible to us, like we cannot with our like naked eye see a proton, and things that are so far away that they're invisible, and also things that are so close that they are visible, and that what exists in the whole cosmos is not limited by our ability to perceive it. And then also the gift that we get from astrophysics and from scientists, where like we are starting to be able to perceive more and more of the entire universe, and that it both expands and kind of reinforces or strengthens our ideas about the universe, scientifically in particular.
Yeah, I love what verse 15 implies about space-time, because of course, if you're the firstborn of creation, you have to be invisible, technically speaking, because there is no one who exists to see you. Like, that's how being visible works. In order to be perceived, there has to be something else to perceive you. And so I enjoyed that part. But also in verse 17, he himself is before all things, and in him all things that hold together. I kind of wonder, is that implying the existence of the forces that hold the universe together? Is the strong and the weak force implied in that, and electromagnetism and the rest?
Because, those concepts were well known 2,000 years ago, so.
Well, we were aware that the universe holds itself together, and so now we're exploring how.
Yeah.
Sure.
Yeah.
I grew up in a United Church of Christ congregation, and I really enjoyed learning about the way that the people who wrote various pieces of the Bible were connecting with their personal contexts, their communities, sometimes just totally ripping off stuff from folklore from previous
we talked about that some in our cosmology episode of the Babylonian mythology around the creation of the universe and Genesis.
And the way that people use metaphors to connect with their personal understanding of the divine. I always find that really, really fascinating, and that's something that I really enjoy about reading scriptures, is the way that people use their personal context, their personal experiences, the way they view the world to talk about the feeling they have with connection with the divine. And I love to see the poetry in that. And I think that if you approach scripture from a strict fundamentalist viewpoint, you miss that, right? Because you constantly have to try to figure out okay, how is this literally true? I know that I'm in a space here where we can talk about it that way, that it wasn't ever it wasn't written to be a history. It was written to be a in many cases, sometimes a form of persuasion, but in many cases an expression of people's own personal connection with the divine, their feelings about life, about existence, about morality, trying to figure out their place in the universe through their understanding. And I find that very relatable, trying to understand one's place in the universe. And I love the way that people use different metaphors and phenomena to try to express that. I think that I've always enjoyed that a lot. I've always been somebody who really enjoys that aspect of, I guess, exegesis, although I don't use that term in polite company generally, because most people I know have not spent time at seminary. But
it's like, well, there's a seminary word, right? But
yeah. So I spoke to you before we started recording about, I did spend some time at a theological school. So I grew up in a UCC church, but I was always really fascinated by just religion in general, like why people believe stuff and how they talk about the divine. And I always had a kind of, I think that most humans on Earth, like not everybody, but most humans have a desire to connect with the divine, to connect with some higher force, being, whatever, some higher purpose. Like, I think that is not fully universal, but very common that people have that feeling. And I think that a lot of times people kind of build religion around that feeling, and that's fine. And I have always felt like I definitely have that. Like, I want to connect with some higher purpose, with the divine in some way. But I also have always had a very strictly scientific worldview in a lot of ways. Like, I appreciate data and evidence. And when I evaluate evidence, like, it's based on like, the tools I have from science and logic. And so I've never had faith per se, because I know that faith is not built around strict adherence to evidentiary principles. Right? Like, and that's kind of the point of it. Yeah. And that's not something that I've ever been able to find. And so although I've always had that desire to connect with the divine, I've never been able to convince myself that it's real. Right. And so, but I do find religious practice very affecting and meaningful. And I love, scripture and ritual to some degree. And so when I was younger, I spent a lot of time kind of going around to different kinds of religious practices and seeing, and experiencing them. And for a long time, based on connections I had through my community, I was going to church on Sunday mornings and synagogue on Friday nights. And like,
there are a lot of people in seminary who do that exact. Like, I used to go to synagogue too. It's
and I loved seeing the different perspective on all these stories that I grew up with. And another thing I loved about that was the kind of much more accountability about personal responsibility for how you deal with people. In a sense, like a focus on like, you can atone to God for sins against God, but if you want forgiveness for sins against other people, you have to actually talk to them and apologize. Mind blowing.
Rabbi Danya Ruttenberg has literally written a book on it, and we'll link to that episode we did with her in the fall.
Cool. But so when I was in college, I was still kind of like, spending a lot of time exploring all these different ideas around faith and religiosity and stuff. And when I applied to grad school to do my PhD, I also applied to seminaries, because I thought what I would do is I would take a year off from science and I would learn about theology, because I was interested in it. I didn't have time for it. And I thought I needed a break from astrophysics, because I thought that going from Caltech physics to Princeton astrophysics would probably kill me.
That's real. I did a different thing with like religious academia.
Yeah. So I deferred admission to Princeton for a year and went to the Pacific School of Religion, which is part of the Graduate Theological Union in Berkeley. It's a UCC seminary, and I enrolled in the Certificate of Theological Studies program, which is a 1-year like academic program. It's not a path toward Master of Divinity. And I took classes on, Old Testament, on theology, biblical Hebrew, sociology of religion, which was absolutely fascinating. And it was really interesting, but I did not stick with it, because what I found was, first of all, I was very frequently kind of sneaking down the hill to Berkeley's astronomy seminars. And I missed doing research. And I didn't really enjoy writing a lot of essays. But the other thing was that I found it kind of frustrating, because all of my classmates had they'd had spiritual experiences, right? Like they had faith and I never did. And I never did find it. And so I found myself getting a little bit frustrated and jealous that all these people had faith, they had religious experiences, that they'd made that connection that I had wanted but couldn't do. And that was part of what had me, dropping out. I dropped out of seminary. I went and did a research project at Cambridge University for a few months.
Like you do.
And then I went to grad school at Princeton. But it was an interesting experience because I learned a lot, and it was really, it was really nice to be able to spend that time thinking about things differently, looking at the universe in a slightly different way and connecting with a different community. But yeah, I never got a degree from it. It doesn't appear on my CV or anything. I don't talk about it very often, but I have always found this stuff really fascinating. Like, why do people believe stuff? What do they believe? How do other people make that connection with the divine? Like, it's really interesting to me.
Yeah. And now for our most out of this world segment. Our Muppets moment. So in this season, we've been asking a different Muppets question for each of our episodes, depending on the topic. And so I am curious, Katie, for your professional opinion, if a Muppet was going to be a space phenomenon, which one would they be? Or alternatively, if a space phenomenon was going to be a Muppet, which?
Right. I think for this, I'm picking pulsars. So pulsars are these rapidly spinning neutron stars. So a neutron star is the very dense remnant of a collapsed massive star, and they often have strong magnetic fields, and they rotate on their spin axis, but that's not always the same as their magnetic field axis, and so it can create these giant jets of radiation that shoot out from the poles the spin of the magnetic axis of the star. And so when the star spins around, it sweeps this like beam of radiation around in a kind of cone on either side. And so if we are in the right position relative to the pulsar, that beam will sweep across us at regular periods. And so you can get, some pulsars are like every few seconds you get a pulse, some it's like milliseconds, you get boop, 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 And so we can pick up these radio pulses and sometimes visual light as well from these spinning stars. And I love the idea of a Muppet being like, just like spinning around and like flashing light. Anyway,
it feels very,
I envision.
Yeah, it feels very animal of me. Animal the Muppet of just like feels very chaotic and also exactly. There's a pattern to the chaos.
I mean they're very regular, but like the very frenetic, I guess is the term.
Yeah.
Sure.
Kay, did you have?
Well, I suppose this isn't technically just a space phenomenon, but I am, you might say, attracted to the idea of Kermit as gravity. Because he is the one that pulls all the Muppets together, and even when someone tries to leave the group, usually they cannot quite manage escape velocity and they wind up getting pulled back in. And it seems like all of the other Muppets orbit around him. And that is what makes the Muppets who they are. So
I like that. My immediate thought, because we've been talking about Cookie Monster in our house a fair amount, was Cookie Monster as Earth to be close to the moon because of the C is for cookie, that's good enough for me. But then there's a point where it's and a C looks like, or a cookie with a bite out of it looks like a C, and the moon looks like a cookie with a bite out of it. And so I could definitely see, and he's blue, right? So the blue of the Earth, and I could definitely see that as a potential Muppety magical thing. I was trying to figure out who would be a supernova, because I feel like Miss Piggy would want to be a supernova. But I don't know if I would cast her. I don't know if I would pick her for the supernova.
No, because a supernova has one big bright flash and then it's over, and that is not Miss Piggy.
Oh, right. That's true. That's true.
So, yeah. So, Katie, any other thoughts on life, the universe, and everything?
I think we covered a lot. I think that there's a lot to discover and appreciate and enjoy about the universe, and I'm just happy that I get to do that.
Yeah. We are too.
Absolutely. All right. Well, thank you so much for joining us. We've had a wonderful time.
Thanks for having me.
And thank you to our listeners for joining us. Theme music was by Rachel Meyer-Laughlin, Muppets music was by Brenda Boss, and seasonal artwork was by Pace Warfield. Catch us next time when we'll dive into astronomers. This podcast has been produced by us, Kay Rohloff and Emily Ewing. For more fun, check us out on Twitter, Facebook, and Blue Sky at Nerds at Church, or contact us at nerdsatchurch@gmail.com.
Also, if you like what you've heard, rate us or leave us a review on Apple Podcasts, Facebook, or wherever you catch your podcasts. If you want access to our uncut episodes, merch discounts, movie commentaries, and more, support us on Patreon at patreon.com/nerdstatchurch. Starting at just $5 per month, it is much cheaper than an entire education in astrophysics.
I would imagine. Also, let us know on Blue Sky, Facebook, or Twitter which Muppet would be which space phenomenon. We would love to hear.
As the ancient Christian said, Pax
Pax
vobiscum.
vobiscum.